Something changed. On October 29th, 2025, as the interstellar visitor known as 3I Atlas reached its closest point to our Sun, it did something unexpected. Something that has left astronomers scrambling for explanations. And what they're discovering now is making some scientists ask questions they never thought they'd have to ask. This isn't about another comet passing through our solar system. This is about an object that traveled for billions of years through the darkness between stars. An object that shouldn't behave the way it's behaving. And the more data we collect, the stranger it gets. Let me tell you what's happening right now. Because what unfolded in the last few days has changed everything we thought we understood about this visitor. As 3I Atlas approached perihelion, its closest encounter with our Sun, something extraordinary occurred. The comet's brightness didn't just increase gradually as expected. It exploded. The brightness surged at twice the rate it had been increasing before. Twice as fast. Astronomers Chi-Cheng Zhang from Lowell Observatory and Carl Battams from the U.S. Naval Research Laboratory documented this phenomenon in real time, and they had no immediate explanation for what they were witnessing. Think about that for a moment. This object has been traveling through interstellar space for what could be billions of years. It has passed through environments we can barely imagine. And now, as it gets close to our Sun, it suddenly becomes dramatically more active than any model predicted. Why? The spectrum analysis revealed something fascinating. The comet's light became bluer than the Sun's own spectrum. This blue shift indicates the presence of carbon molecules, specifically C2, and amidogen compounds, NH2. These are signatures of active ice sublimation. But here's what makes this unsettling. Radio observations detected that in just 2 weeks before perihelion, 3I Atlas was losing approximately 5.7 times, 10 to the 28th power water molecules per second. That's 40 times more than it was losing just 1 month earlier. 40 times more water pouring out into space, like, as one scientist described it, a fire hose on full blast. Now, you might think this is normal comet behavior. Comets heat up near the Sun, ice turns to gas, they get brighter. Standard physics. Except 3I Atlas isn't following standard physics. The rate of change is wrong. The timing is wrong. And what we're seeing doesn't match what we know about comets from our own solar system. Here's where it gets interesting. Space-based telescopes, SOHO, Stereo A, and the new GOES-19 satellite, all equipped with coronagraphs that can observe objects close to the Sun, captured images of 3I Atlas during this critical period. And what they saw was unusual. The comet appeared as a faint but noticeably elongated spot. But here's what's strange. It had no visible dust tail. None. Just this stretched out glow without the characteristic dust trail that comets normally produce. What does that mean? Well, some scientists have proposed that initially, carbon dioxide gas was escaping from the comet at a distance of about 3 astronomical units. This CO2 would have been cooling the surface of the nucleus, essentially acting as a protective layer that prevented water from sublimating. But then, something changed. That protective layer depleted. And when it did, the water ice underneath was suddenly exposed to direct solar radiation. The result? An explosive increase in brightness and activity. But there's another possibility. And this is where things get uncomfortable for some researchers. The composition of 3I Atlas's nucleus might be fundamentally different from anything we've seen before. Remember, this object didn't form in our solar system. It formed around a different star, in a different stellar environment, with different chemical conditions. What if its internal structure is nothing like the comets we're familiar with? What if there's something inside that nucleus that we don't understand yet? The James Webb Space Telescope has been observing 3I Atlas, and what it found adds another layer to this mystery. Webb's near-infrared spectrograph revealed that this comet has been transformed by billions of years of cosmic ray bombardment. We're talking about galactic cosmic rays, high-energy particles that permeate interstellar space, striking the comet's surface continuously for eons. According to research led by Romain Maggiolo from the Royal Belgian Institute for Space Aeronomy, these cosmic rays have fundamentally altered the physical and chemical structure of 3I Atlas. Computer simulations suggest that cosmic rays have penetrated approximately 50 to 65 feet deep into the comet's surface, creating what scientists are calling a deep irradiated crust. This crust no longer resembles the pristine material from the comet's home star system. It's been cooked by radiation for so long that it's become something else entirely. Here's the paradigm shift. Scientists have been hoping that interstellar objects like 3I Atlas would give us a window into other stellar systems, that we could analyze these visitors and learn what conditions are like around distant stars. But if Maggiolo is right, what we're looking at isn't a pristine sample from another star system. It's a heavily modified, radiation-processed shell that has been fundamentally changed by its journey through interstellar space. Maggiolo said something that should make us all pause. He said that 3I Atlas is now a product of its interstellar journey rather than where it came from, at least on the outside, which raises an obvious question. What's underneath that irradiated crust? What's hidden in the core of this object that might still be pristine material from its origin system? And here's something most people don't know. Professor Avi Loeb, the former chair of Harvard's astronomy department, has formally requested that NASA release all scientific data on 3I Atlas to the public. Why would he do that? What does he think might be in that data that NASA hasn't shared yet? The behavior of 3I Atlas after perihelion is now the focus of intense scrutiny. Scientists admit they don't know what will happen next. Will the brightness continue to increase? Will it suddenly fade? Zhang and Batoms noted in their observations that the comet's evolution after perihelion could be just as unusual as the outburst that preceded it, maybe more unusual, and that uncertainty is what makes this moment so critical. We're watching in real time as an object from beyond our solar system does something we can't fully explain. At perihelion, 3I Atlas reached a visual magnitude of approximately 9. That's bright enough to be visible through small amateur telescopes, if you knew exactly where to look. But here's the thing. It was positioned so close to the sun in our sky that observing it from Earth's surface was nearly impossible during that crucial moment. We had to rely on space-based coronagraphs to see what was happening. And what they showed us was an object that looked nothing like a typical comet. The images revealed this elongated, glowing form without the expected dust tail. Instead, what we're seeing appears to be primarily gas emission. The hydroxyl glow, the signature of water vapor escaping from the comet, was detected by NASA's Swift Ultraviolet SH optical telescope. But the lack of visible dust, that's anomalous. Comets produce dust. It's what makes their tails so spectacular. So, where's the dust from 3I Atlas? One possibility is that the composition is fundamentally ice-rich, with very little solid material to produce dust. But that doesn't fully explain the explosive brightening. Another possibility, and this is where some researchers get uncomfortable, is that the object's internal structure is unlike anything we've classified before. Now let's talk about what the James Webb Space Telescope revealed, because this is where the story takes a turn into territory that challenges our assumptions about interstellar objects. Webb observed 3I Atlas back in August, before the perihelion passage. The near-infrared spectrograph instrument analyzed the light coming from the comet, looking at the specific wavelengths that tell us what molecules are present. The data confirmed something that earlier observations had hinted at. This comet is rich in carbon dioxide. Unusually rich. But more importantly, Webb's analysis revealed that the outer layers of this object have been fundamentally transformed by cosmic radiation. Here's what that means. In our solar system, we have a protective bubble called the heliosphere, created by the solar wind streaming out from our sun. This heliosphere shields us from most galactic cosmic rays, those high-energy particles that come from supernova explosions and other violent events across the galaxy. But in interstellar space, there is no such protection. Objects drifting between the stars are exposed to the full intensity of cosmic ray bombardment for millions or billions of years. Computer models developed by Maggiolo and his team, adapted from earlier studies of our local comets, simulated what happens to ice and rock when it's exposed to cosmic rays for extended periods. The simulations showed that after approximately 1 billion years of irradiation, the transformation is complete. The outer layers become something different. Carbon monoxide converts to carbon dioxide. The crystalline structure of the ice changes. Chemical bonds break and reform in new configurations. The result is a crust that extends roughly 50 to 65 feet into the comet's interior. A shell of radiation-processed material that no longer represents the original composition from the comet's birth system. And here's the unsettling part. We don't know how thick this crust really is. We don't know if solar heating will erode it away to reveal pristine material underneath, or if the entire object has been transformed all the way through. Maggiolo stated clearly that scientists need to take these aging processes into account when analyzing 3I Atlas. You can't just assume you're looking at a fresh sample from another star system. You're looking at something that has been modified by the harsh environment of deep space. But he also said something hopeful. He said 3I Atlas remains very interesting despite this complication. Because if we can understand how the radiation crust formed, and if we can compare observations from before perihelion with observations after, when solar erosion might have exposed deeper layers, we might still be able to glimpse the original composition. That's what scientists are waiting for now. The comet has passed perihelion. It's moving away from the sun. And in November and December of 2025, right now, it will become visible again from Earth as it continues its trajectory out of our solar system. This is our window. This is when we might see if the solar heating stripped away enough of that radiation crust to reveal what's underneath. But there's something else happening. Something that doesn't fit neatly into the standard narrative of a comet being a comet. Susanne Falsner, a professor at Forschungszentrum Jülich in Germany, has proposed something radical about interstellar objects like 3I Atlas. She suggests these objects might not just be cosmic debris. They might be the seeds of planets. Her computer models show that young stars, surrounded by their planet-forming disks of gas and dust, could capture millions of interstellar objects as they drift through the galaxy. And once captured, these objects, already hundreds of meters in size, could serve as the nucleus around which planets grow. This solves a long-standing problem in planetary science. We know that planets form through accretion, small particles sticking together to form larger and larger objects. But there's a gap in our understanding. Computer simulations show that once objects reach about a meter in size, the chaotic environment of a protoplanetary disk should cause them to collide and shatter rather than stick together. So how do you get from meter-sized rocks to planet-sized worlds? Falsner's answer is simple. You don't start from meter-sized rocks. You start from interstellar objects that are already large enough to gravitationally attract material and begin the planet-building process. Interstellar space delivers ready-made seeds for the next generation of planets. And here's the kicker. Her models suggest this process works especially well around massive stars, stars larger than our sun, which would explain why gas giant planets like Jupiter are more commonly found around larger stars, even though the planet-forming disks around those stars only last about 2 million years. Too short a time for traditional planet formation theories to work. So when you look at 3I Atlas, you're not just looking at a comet. You're potentially looking at the kind of object that could have become a planet if it had been captured by a young star billions of years ago. You're looking at a building block of worlds that never got built. And that changes the entire context of what we're observing. But let's return to what's happening right now, because the most intriguing aspect of this story isn't just what we've discovered. It's what we still don't know. The trajectory of 3I Atlas is unusual. It's traveling at over 130,000 miles per hour relative to our solar system, moving in what observers have described as an unusually flat and straight path. This isn't the chaotic, curved trajectory you'd expect from an object that formed in our solar system and has been influenced by planetary gravity for billions of years. This is a trajectory that screams, "I came from somewhere else, and I'm just passing through." Some estimates suggest 3I Atlas could be around 7.5 billion years old. That would make it approximately 3 billion years older than our entire solar system. Think about that. This object existed before our sun ignited, before Earth formed, before any of the planets we know came into being. It has been traveling through the galaxy since a time when the Milky Way looked completely different than it does today. What has this object seen? What environments has it passed through? What stellar systems did it drift by in the darkness? Never quite close enough to be captured, but close enough to be influenced by their radiation, their stellar winds, their cosmic neighborhoods. We know it came from somewhere in the galactic frontier, possibly from the outer regions of the early Milky Way. But we don't know where it formed, what star it orbited, or what happened to that star. We don't know if it was ejected from a young planetary system by the gravitational interactions of forming gas giants, or if it simply condensed in the space between stars and has been wandering ever since. What we do know is that right now, at this very moment, 3I Atlas is moving away from our sun, heading back out into the darkness. And we have a limited window to gather as much data as possible before it fades from view forever. Once it leaves, we'll never see it again. This is a one-time opportunity, and that brings us back to Avi Loeb's request to NASA. Professor Loeb has been vocal about the need for transparency when it comes to interstellar objects. He was one of the leading voices calling for serious scientific investigation of Oumuamua, the first confirmed interstellar visitor, which passed through our system in 2017. Loeb suggested then, and maintains now, that we should not dismiss unusual possibilities when confronted with unusual data. He argued that Oumuamua's elongated shape, its unexpected acceleration as it left the solar system, and its lack of visible cometary activity were all anomalies that deserved rigorous investigation rather than rushed explanations. Now, with 3I Atlas, Loeb is calling on NASA to release all scientific data to the broader research community and the public. His argument is straightforward. This is an object of extraordinary scientific importance. It's only the third confirmed interstellar visitor we've ever detected. The data collected by NASA's instruments, by the Swift Telescope, by SOHO, Stereo, and GOES 19, represents humanity's best chance to understand what interstellar objects are really like. That data shouldn't be siloed. It should be available for independent analysis by researchers around the world. But there's an unspoken question underneath Loeb's request. What exactly is in that data? What has NASA observed that hasn't been publicly discussed? Are there measurements, spectra, or behavioral patterns that don't fit easily into press releases and preliminary papers? The scientific community is divided on how to interpret 3I Atlas. Some researchers are comfortable with the explanation that it's simply a comet with an unusual composition, modified by cosmic radiation, behaving in ways we haven't seen before because we've never studied an interstellar comet this closely. They point to the carbon dioxide, the water vapor, the molecular signatures that all say, this is a comet, just a weird one. But others are less certain. They point to the anomalies, the explosive brightening that doesn't match models, the missing dust tail, the perfectly flat trajectory, the possibility that its internal structure is fundamentally different from anything in our cosmic neighborhood. And they ask, quietly, in research papers and conference presentations, what else could explain these observations? No one is saying it outright. No one wants to be the scientist who jumps to conclusions without evidence. But the questions are there, hanging in the air like the comet's own glowing tail. What if 3I Atlas isn't entirely natural? What if there's something about its composition, its structure, or its behavior that suggests it's more than just a ball of ice and rock that's been drifting through space for billions of years? Here's what makes that question so uncomfortable. We have no framework for answering it. Our entire scientific understanding of comets, asteroids, and interstellar objects is based on natural formation processes. We look at spectra, we see carbon dioxide and water, and we think comet. We see an elongated shape, and we think fragment from a planetary collision. We see a trajectory, and we calculate gravitational interactions with other stellar systems. But what if the signatures we're trained to interpret have multiple possible explanations? What if some of the things we're seeing could be consistent with both natural and artificial origins? How would we even know the difference? This is not about declaring 3I Atlas is anything other than what it appears to be. This is about acknowledging that our sample size for interstellar objects is exactly 3. Oumuamua, Borisov, and now 3I Atlas. 3 objects out of the potentially billions or trillions of objects drifting through our galaxy. We're drawing conclusions about an entire class of cosmic phenomena based on 3 examples. That's not science. That's preliminary observation at best. And each of those 3 has presented us with surprises. Oumuamua accelerated in a way that couldn't be explained by outgassing alone. Borisov was relatively normal, but came from a different stellar environment with different chemical signatures. And now, 3I Atlas is brightening explosively, losing water at unprecedented rates, and challenging our models of how irradiated comets should behave. Maybe all 3 are just natural objects with unusual properties. Maybe the universe is far more diverse than we've given it credit for, and every interstellar visitor will teach us something new about the variety of environments and formation processes across the galaxy. That's the simplest explanation, and it's probably correct. But the explosiveness of 3I Atlas's brightening, the timing of it, the way it happened right at perihelion, that keeps nagging at some researchers. Because there's a difference between unusual but explainable and unusual in a way that suggests something we haven't considered. Let's talk about what happens next, because the story of 3I Atlas is far from over. As the comet moves away from the sun, it will remain observable through November and December. Astronomers around the world are pointing their telescopes at it, collecting spectroscopic data, measuring its brightness, tracking any changes in its activity level. The question everyone wants answered is simple. Will the activity decrease now that it's moving away from solar heating? Or will something else happen? Zhang and Batums specifically noted that the post-perihelion evolution could be just as unusual as the pre-perihelion outburst. What did they mean by that? What are they expecting? Or perhaps more accurately, what are they concerned might happen? One possibility is that the comet will simply fade as expected. The solar heating decreases, the sublimation slows down, the brightness drops, and 3I Atlas becomes a dim speck gradually disappearing into the darkness. That would be the normal scenario. Another possibility is that the activity continues or even increases. If there's something inside the nucleus, some volatile material that's now been exposed by the erosion of the outer layers, it could continue outgassing even as the comet moves away from the sun. That would tell us the internal composition is radically different from the surface. But there's a third possibility that no one wants to say out loud. What if the behavior changes in a way that can't be explained by solar heating at all? What if there's a pattern to the activity that suggests internal processes rather than external heating? What would that mean? The 2 Mars rovers, Curiosity and Perseverance, actually had a unique opportunity to observe 3I Atlas from their vantage point on the Martian surface. Their observations provided a different perspective, a different angle of view that could reveal details invisible from Earth. The data from those observations hasn't been fully released yet. What did they see? Here's something most people don't realize. The comet came close enough to the sun that the solar wind, that stream of charged particles flowing out from our star, would have interacted directly with its coma, the cloud of gas and dust surrounding the nucleus. That interaction creates effects we can observe: plasma instabilities, magnetic field distortions, particle acceleration, and those effects can tell us about the composition and structure of the comet in ways that simple spectroscopy cannot. NASA's STEREO mission, specifically designed to study the sun and its influence on the space environment, captured images showing 3I Atlas interacting with the solar wind. Those images revealed structures in the coma, asymmetries in the gas distribution, patterns that suggest complex dynamics at play. But interpreting those patterns requires understanding not just cometary physics, but plasma physics, magnetohydrodynamics, and the chaotic environment near the sun. This is why Loeb's call for data transparency matters. The more eyes on this data, the more perspectives brought to bear, the better chance we have of understanding what's really happening. Maybe one research group will notice something another group missed. Maybe an independent analysis will reveal a pattern that changes the entire interpretation. Science works best when it's open, when data is shared, when unusual observations are met with rigorous analysis rather than premature dismissal. And 3I Atlas is unusual enough that it deserves that level of scrutiny. Now let's address something that's been circulating in online discussions and amateur astronomy forums. Some people have noted that the timing of 3I Atlas's outburst, coinciding almost exactly with perihelion, seems too precise. Natural processes are often messy, chaotic, with gradual changes rather than sudden transitions. So why did the brightness surge happen exactly when it did? The scientific explanation is that there was a threshold effect. As the comet heated up, it reached a critical temperature where the sublimation rate suddenly increased. The protective CO2 layer depleted at a specific point, and once it did, the water ice underneath was exposed all at once, leading to the rapid brightening. That's plausible. That fits known physics, but there's an alternative interpretation that some find compelling. What if the object was designed to activate at a specific distance from a star? What if the outburst wasn't caused by passive heating, but by some internal process triggered by proximity to our sun? Before you dismiss that as science fiction, consider this. We've already sent probes to other planets that activate at specific times or under specific conditions. We've built satellites that wake up when they detect solar radiation above certain levels. The concept of a threshold-triggered system is not exotic. It's basic engineering. The question isn't whether such a thing is possible. The question is whether there's any evidence that 3I Atlas is anything other than a natural object. And the honest answer is, we don't have enough data yet to rule anything out conclusively. What makes 3I Atlas particularly intriguing is its mass. Early estimates suggest this object has a mass of approximately 33 billion tons. That's enormous for a comet. Most comets we observe from our own solar system are much smaller. The nucleus of Halley's comet, for comparison, is estimated at around 22 billion tons. So 3I Atlas is significantly more massive than one of the most famous comets in human history. Now, mass alone doesn't mean anything unusual. Larger objects exist throughout the solar system, but combined with the other anomalies, the high velocity, the explosive outgassing, the unusual trajectory, it adds another data point to a growing list of things that make this object stand out. And then there's the velocity. 130,000 miles per hour might not sound extraordinary in cosmic terms, but it represents a specific energy state. This object is moving fast enough to escape not just our solar system, but to travel between stellar systems over billions of years. It's been in transit for so long that the star it originated from might not even exist anymore. That star could have evolved off the main sequence, swelled into a red giant, shed its outer layers, and collapsed into a white dwarf, all while 3I Atlas was wandering through the darkness. Think about that journey. 7.5 billion years. If the age estimates are correct, this object has been traveling since before complex life existed on Earth. It passed through regions of space we can only theorize about. It survived encounters with who knows how many stellar systems, gravitational perturbations from massive objects, radiation from sources we can't identify. And it emerged from all of that intact, still coherent, still recognizable as a discrete object rather than a dispersed cloud of debris. That in itself is remarkable. The survival rate for objects traveling through interstellar space over billions of years should be relatively low. Collisions with other objects, gravitational disruptions, radiation damage that causes structural failure, all of these are threats. Yet 3I Atlas is here, apparently intact, apparently functioning in ways that suggest it's held together remarkably well despite its ancient origins. The irradiated crust that Webb detected might actually be part of the answer. That 50 to 65 foot thick layer of radiation processed material could be acting as protective armor, shielding the interior from further damage, maintaining structural integrity. It's a shell forged by billions of years of cosmic ray impacts, harder and more resistant than the pristine ice underneath. In a sense, the journey itself made 3I Atlas more durable. But here's where it gets interesting from an engineering perspective. If you were designing a probe to travel between stellar systems, to survive the harsh environment of interstellar space for billions of years, what would you do? You'd need protection from radiation. You'd need structural integrity that could withstand micrometeorite impacts. You'd need a design that could handle extreme temperature variations. And you'd probably want it to be mostly passive, not requiring active systems for the majority of the journey, only activating when it encountered specific conditions. An irradiated crust would serve many of those functions. It would protect the interior. It would provide structural strength. It would be formed naturally by the environment, requiring no active maintenance. And if there was something underneath, something that needed to remain dormant until triggered by proximity to a star, that crust would keep it safe. Now, I'm not saying that's what 3I Atlas is. I'm saying that if you look at the characteristics we've observed, the age, the mass, the protective crust, the threshold-triggered activity, you're looking at properties that would also be consistent with a designed object meant to travel between stars. That doesn't prove anything. It just means we should be thorough in our analysis. This is why the scientific method exists. You don't start with conclusions. You gather data, you test hypotheses, you look for ways to distinguish between competing explanations. And right now, we need more data. The observations coming in over the next few weeks will be critical. If 3I Atlas fades predictably, if its behavior matches refined models of irradiated comets influenced by solar heating, then we'll have a good natural explanation for everything we've seen. The anomalies will be explained as the result of unusual but understandable composition and environmental history. But if the behavior continues to deviate from predictions, if there are patterns in the activity that don't correlate with solar distance, if the spectroscopic data reveals compositions or structures that challenge our understanding of natural comet formation, then we'll need to expand our hypothesis space. We'll need to consider possibilities that currently seem unlikely. And that's uncomfortable for many scientists, because once you start entertaining hypotheses that fall outside the conventional framework, you open yourself up to criticism, to accusations of speculation, to being labeled as fringe or sensationalist. But that discomfort shouldn't prevent us from following the data wherever it leads. Loeb has been vocal about this. He's argued repeatedly that the stigma around discussing non-natural origins for unusual objects is itself unscientific. Science is supposed to be agnostic about outcomes. You propose hypotheses, you test them against evidence, and you follow the results. If an artificial origin hypothesis can be tested and falsified, then it's a valid scientific hypothesis, regardless of how uncomfortable it makes people. The challenge is figuring out what observations would actually distinguish between natural and artificial origins. What would we expect to see differently? What measurements, what patterns, what signatures would be diagnostic? For a natural comet, we'd expect activity to correlate directly with solar heating. We'd expect the composition to fall within known ranges for ices and rocks formed in protoplanetary disks. We'd expect structural variations to be random, reflecting chaotic accretion processes. We'd expect the trajectory to show small perturbations from outgassing that match the direction and intensity of observable jets. For something designed, we might expect precise threshold behaviors, activity that switches on or off at specific conditions rather than gradually changing. We might expect unusual symmetries in the structure or composition. We might expect trajectory corrections that can't be explained by passive outgassing. We might expect radio emissions at frequencies that suggest modulation rather than natural plasma processes. Have we looked for those things? Have we conducted the tests that would allow us to distinguish between these possibilities? That's what Loeb is asking NASA to provide data for. Let the scientific community examine everything. Let independent researchers look for patterns. Let the analysis be as comprehensive as possible. Because here's the reality. We are living in a moment of cosmic significance. For the first time in human history, we have the technology to detect, track, and analyze objects from other stellar systems. We can point our most advanced telescopes at these visitors and gather data that would have been impossible even 20 years ago. The James Webb Space Telescope, launched just a few years ago, is giving us insights into the composition and structure of objects at unprecedented resolution. Our network of space-based observatories provides continuous monitoring that ground telescopes alone could never achieve. This is the golden age of interstellar object research, but it's also a brief window. These objects pass through quickly. 3I Atlas will be gone within months, disappearing back into the vast emptiness between stars, and we may never see another interstellar visitor for years or decades. Each one is precious. Each one is an opportunity we can't afford to waste. And that's why the explosive brightening matters. It's why the missing dust tail matters. It's why the radiation crust matters. It's why every anomaly, every unexpected behavior, every deviation from our models deserves serious attention. Because we're not just studying a comet. We're gathering data that could reshape our understanding of what exists in interstellar space. Think about the implications if interstellar space is filled with objects like 3I Atlas. Billions upon billions of them, drifting between the stars, carrying within them the chemical signatures of distant stellar systems, possibly even carrying the building blocks of planets yet to form. The galaxy becomes a vast ocean of potential, of raw material constantly in motion, constantly redistributing itself across light years. But think about the implications if even a small fraction of those objects are something else. If among the countless natural comets and asteroids wandering through the darkness, there are also artifacts, probes, constructs sent out by civilizations that existed millions or billions of years ago. What would that mean for our understanding of intelligence in the universe? What would it mean for our place in the cosmic story? We've searched for radio signals from the stars. We've looked for laser pulses, for engineered structures around distant suns, for any sign that we're not alone in this vast universe. But maybe we've been looking in the wrong place. Maybe the evidence isn't out there among the stars. Maybe it's here, passing through our own solar system, disguised as natural objects, because that's exactly what they're made of. Interstellar probes wouldn't look like spaceships from science fiction. They'd look like rocks, like ice, like comets. They'd blend in. And the only way we'd know the difference is through careful, detailed analysis of their behavior and composition. Which brings us back to the data. Which brings us back to transparency. Which brings us back to the fundamental question of whether we're being as thorough as we should be in investigating these objects. The next few weeks will tell us a lot. As 3i Atlas moves away from the Sun, as we continue to monitor its brightness, its spectrum, its trajectory, we'll gather more pieces of the puzzle. Maybe those pieces will fit together into a clear picture of an unusual but entirely natural comet. Maybe they'll reveal patterns that challenge our current understanding and force us to expand our theories. Or maybe, just maybe, they'll show us something we weren't expecting. Something that makes us question our assumptions about what's possible, about what exists out there in the darkness, about whether we're as alone as we've always believed. One thing is certain: we're watching. Right now, at this moment, telescopes around the world and in space are pointed at 3i Atlas. Scientists are analyzing spectra, calculating trajectories, modeling internal structures. Amateur astronomers are sharing observations, comparing notes, contributing to a global effort to understand this visitor. The data is accumulating. The picture is becoming clearer. And whatever we discover, whatever the answer turns out to be, it will change something about how we see the universe. Because every interstellar object teaches us something new. Every visitor from the darkness brings with it information we couldn't obtain any other way. Every anomaly is an opportunity to refine our theories, to test our assumptions, to push the boundaries of what we know. 3i Atlas came from somewhere. It traveled for billions of years to reach us. It survived conditions we can barely imagine. And now, for a brief moment in cosmic time, it's here, close enough for us to study, close enough for us to learn from. It's performing in ways we didn't predict, behaving in ways that challenge our models, revealing properties that force us to think harder about what interstellar objects really are. The question isn't whether 3i Atlas is strange. It clearly is. The question is what that strangeness means. Is it the strangeness of a natural universe, more diverse and complex than we've given it credit for? Or is it the strangeness of something else, something that makes us reconsider fundamental assumptions about our place in the galaxy? Time will tell. The data will tell. And that's why we need all of it. That's why transparency matters. That's why Loeb's request to NASA is important, regardless of what the final answer turns out to be. Because in the end, this isn't just about one object passing through our solar system. It's about how we approach the unknown. It's about whether we're brave enough to follow the evidence wherever it leads, even if it takes us to uncomfortable places. It's about whether we're willing to ask difficult questions and accept uncertain answers. 3i Atlas is still out there, moving away from us at over 100,000 miles per hour, carrying its secrets back into the darkness. But for now, for these precious weeks while it's still visible, we have a chance to learn, to observe, to question, to wonder, and maybe, just maybe, to discover something that changes everything. The interstellar visitor has arrived, has performed its unexpected display, and is now departing. What it leaves behind is questions. Important questions. Questions that deserve answers. The universe is speaking to us through these objects. Are we listening carefully enough to hear what it's saying?